So last time we started looking a little bit at query optimization, and there are these two words in query optimization I explained to you. One is the rule-based optimization, or also called heuristic optimization, and the other is cost-based optimization. So last week it was heuristic optimization. You apply a set of rules. Here again was the example. That's a super complex algorithm consisting of 2 lines of code. Yeah? So you have a canonical plan that is a one-to-one translation from your SQL statement. You have a set of rules, and then you try to apply those rules one by one to modify the plan. Of course, you may only modify the plan in a way that the result of the plan does not change. Yeah? So semantically, it must always be the same plan you're looking at. And then we had these rule sets consisting of these 2 things. One is this match function, and the other is a modify function. So match means you look at a pattern you find in a tree, in an incoming plan, specified here. So that's an operator tree. That's another word, another name for a plan. Yeah, so you analyze a plan and try to find out whether there's a certain pattern you can do something with. Yeah? And if that is the case, you execute that modify operation. And then, as examples, we had stuff like this. So a match condition could be, is there a selection with a conjunction and the predicate? Yeah, so A equals 4 and B equals C. Then you can basically break up this conjunction into 2 separate selection operators. And that would allow you to apply other rules later on, like to push down one of those to a specific branch. Or another rule would be something like this. Is there a selection with a join predicate directly above a cross product? That was an important rule we looked at. Then you can rewrite this stuff to a join operator, a real join operator, not simply a cross product. And the join operator would be way more efficient than the squarish cross product, of course. Yeah, that's the stuff we looked at. And we looked at different transformation rules, so the most important being the predicate pushdown, of course. There were others, and so forth and so forth. So this week we are looking at cost-based optimization. And so the initial condition is the same. Yeah, so we have this logical plan. Somehow it may be that the logical plan was transformed by rule-based optimization or not. You could also start directly with a canonical representation. But basically what we are doing today is we want to enumerate alternatives. And alternatives really means, I mean, assume you want to go shopping. Yes, you have 3 supermarkets you are aware of. Yeah, and then you can make a cost estimate. Okay. Going to the supermarket in Saarlouis is like 40 minutes by train, but the supermarket is way cheaper. Yeah? What is the total cost of doing that? Yeah? Traveling by train, 40 minutes to Saarlouis. Everything is cheaper there in the supermarket, and then you go 40 minutes back, so you can make the overall calculation. So am I willing to invest 2 times 40 minutes by train at the benefit of paying less in the supermarket? Or you go to somewhere downtown Saarbrücken, maybe it's much more expensive, but you don't have to sit 80 minutes on the train, yeah, and then you can do the math. Yeah? You make a cost estimate. Yeah? You make a cost estimate for these, those were 2 alternatives, think about a third alternative, whatever, go shopping here on campus, yeah, and you make a cost estimate, and then you make a decision. Then you actually go to one of those supermarkets. And it's the same idea we're doing in query optimization. So we enumerate, we list all the alternative plans, make cost estimates, but then only go for one of those plans. That's the idea in cost-based optimization. Yeah? So enumerating alternatives, costing them, yeah? So making a cost estimate and then going for one of those plans. So typically what the optimizers try to achieve is this one. Yeah? Only the plan with the expected shortest runtime is executed. If your cost model is runtime, yeah, whatever minimizes the cost model, you want to identify the plan that has the lowest cost in your cost model. If that is runtime, okay. If that is energy consumption, okay. If that is I/O, writing stuff to disk or over the network, maybe that is what you define as lowest costs. Yeah, whatever you defined as a cost model. And this is the difference, and this is important to understand. That's the difference to part 1 last week. So last week was this one. Yeah? So we started with a plan. Yeah, then we had this iterative application of rules. Yeah, iterate, iterate, iterate. But at that point, so in this iteration algorithm, in rule-based optimization, we never look at costs. We never do a cost estimate for those plans. We just apply the rule. We know that predicate pushdown, projection pushdown will be better in 99.99999% of the cases. So we just do it without worrying whether the resulting plan is better or not. It's the same for replacing a cross product by a join. In most situations, a join will be better. There are corner cases where the cross product is actually better. For instance, if the inputs are really, really small, and the cross product is slightly better. So it's not a perfect method, but it's a method that turns out to work well in practice. And now we're here, and now we are entering a world where it's not that easy to make those decisions. So we will see there are so many options to transform this plan into maybe plan 42A, B, C, or D, but we can't decide for which plan to go without making a cost estimate. And that is what cost-based optimizers do. So they enumerate this huge space of alternatives, run, then compute the estimated costs for the alternatives, and eventually, let's hope for the best, they come up with a plan with a lowest estimated cost under the cost model. And that's a different planet here, because this is without costs, and that is with costs. And also the search space here typically on the right can be rather big. That's one really practical problem you will see. Okay. Here again in more text form. So what are the different dimensions of cost-based optimization? There are decisions on the logical level and the physical level. If you think about, we have this logical operators, the Greek letters and join symbol and stuff. And we have the physical operators, like how is a join algorithm implemented? How is an index, how is a selection implemented through a scan or through an index access? These kind of decisions. So on the logical level, we can make decisions on the join order. So which join order has less runtime? Should I first join S and T, and whatever the result is with R? That could be one option. Or maybe it's better to first join R with S, and then the result of that join operation with T. Maybe one of these alternatives is cheaper than the other, so I want to pick the cheaper alternatives. And then there are all kinds of decisions on the physical level. Those are the three major problems or challenges, let's phrase it like that. So one is which physical operator to use, so which algorithm to use. Is it hash-based, is it sort-based, is it whatever? So there are zillions of join algorithms you could use. You have to make a decision. The system has to make a decision automatically. Today one would say the AI has to make a decision. So we should rebrand all of what database is doing is, all of computer science is AI these days, right? It's not. Okay, it's just an optimization problem. I wouldn't phrase it as AI actually. Okay, so we have to make so the optimizer has to make a decision, and then we looked at that a little bit last time. So use an index or don't use an index. Should I scan the relation? Should I use binary search? Should I use a hash-based the hash table? Should I use a tree like the B tree we learned about last week? And so forth and so forth. So actually we have a notebook on that. I will show that to you in a moment. But let's wrap up with this option number 4, so the challenge number 4. So which resource to use for which subplan? So how many threads do you want to use where, which part of the plan gets how much computing time, main memory, and so forth and so forth. In particular, assume a system where there are multiple queries running at the same time, and you want to compute the results to those queries all at the same time. So which query gets whatever, 90% of the DRAM, and the others only get 1% each, or whatever. Those are all decisions along the lines of resources, how much resources you assign to each of those queries. Use the index or not use the index, that is challenge number 3. So basically, whenever there's a condition like that, you basically have these two options. You use a brute force approach, meaning you scan the input relation. So we examine each tuple in R and check if the predicate, the filter predicate, is true. And if that is the case, we add the tuple to the result set. That's a brute force approach. You can always do that. That's fine. But typically, you want to do something which is much better. That is, let's hope for the best you have an appropriate index, where you can directly go, like in the B tree, fetch the result tuples and don't have to scan the entire relation. In particular for large data sets, so this index option is a way to go and makes a huge difference. Yeah, and with that, I would like to switch to a notebook that shows you a little bit the problems or the issues that occur. So basically, what these query optimizers then have to tackle with is costing certain plans. Yeah? And in this notebook, what we're doing is we have a scenario that looks as follows. I'm showing the join graph here. So that's our, those are the relations. So the bubbles here are the relations A, B, C, and D. And the edges determine the selectivity of those join graphs. Maybe I show this notebook later. Maybe it makes more sense to you if I show it later. Looking at that, maybe first do a little bit more of slides. Makes a lot of sense to show it later, actually. Yeah, it's easier to digest. So first, let's look at these different challenges on the slides, and then we look at the notebook and practical aspects. So join order. So this dimension join order consists of different sub-plans, actually. And one is the tree structure of the plan. If you remember, we only have binary operators. We have unary operators and binary operators, join operators being binary. There's no ternary join operator in this database world. So the question is, how many plans, how many different tree structures do you have given a certain number of input relations? And this is determined by the so-called Catalan numbers. So if you have n input relations, there are Cn-1 many binary trees with n leaf nodes. Yeah, and that is the formula for that. It actually grows exponentially. Yes, you see here number of how this number grows. And here's an example. So assume you have 3 input relations. So this means you have to compute the Catalan number 2, that is 2 plans. So for 3 input relations, there are only 2 options. You first, that's a tree structure like this, and it's a tree structure like that. So this plan is called the left D plan, that is called the right D plan. There are no more options for joining these relations in terms of the tree structure. Yeah? Ignore how these leaves are labeled for the moment. Just if you look at the internal structure of this tree here, those are the 2 options you have for 3 input relations. Yeah, if you have 4 input relations, the space already grows. So we see, okay, we have this left deep structure, we have a right deep structure, we have structures that we call bushy, so something like this, and also the mirrored version of that, and then this symmetric version. Those are the 5 binary tree structures for 4 input relations. Okay? But then the question is, how do I label those leaves? Yeah? So on which edge down here do I write which relation? And there's another I mean, here I have, if you think about it, you have 4 relations. How can you order 4 relations? Yeah, what are the number of ways you can order those relations? That's basically this number. Yeah? So that's, in German, it's a Fakultät, n Fakultät. In English, it's factorial, right, that's a term. So it's n factorial number of orders you can write down different relations here. Yeah? I think I have an example on that. So here's an example for 3 input relations. So for 3 input relations, it's, let's scroll down a bit. For 3 input relations, it's 3 factorial, that is 6. Yeah? 3 times 2 times 1 is 6. So that already is 6 different orders. Those orders are depicted here. And I label them as that's input relation A1, A2, A3, and those are the orders here. So this means for left deep, just for this structure, you have 6 different plans. that become possible, yeah? Because all of these it's basically the number of different orders times the number of the binary tree structures, which happens to be 2. Yeah? So it's these 2 structures times 6, that's this number here, give you 12 different plans theoretically you have to consider. Yeah? And that goes through the roof pretty quickly. You see that with n factorial times times the Catalan number. So basically that is the number of plans you have to consider. And for large queries with many relations, this becomes infeasible to compute actually. Right. Yeah, one thing that you see frequently, and that's also a confusion you see in database research, when people talk about query optimization and what is the optimal plan. I just want to state that now because that is a confusion that exists. The question is, should you consider only joins or should you also consider cross products? Yeah, you could say, I mean, I have my joins defined in the declarative SQL statement. So why should I consider cross products? And to illustrate what I mean, here's a simple example. So assume I have 3 relations. So basically how that looks like technically is you have a central table that is connected to 2 tables. This kind of schema is also called a star schema. So you have a join condition here. This is one join condition between F and D2, and you have a join condition between F and D1, but you don't have a join condition here between D1 and D2. There's no join predicate specified in the query. Okay, so actually you have a structure like that. And now the question is, okay, theoretically, if you look at enumerating these 3 relations, of course you have these 2 options, yeah, as shown above. Maybe we can go back to that example. Right, here it's 3 relations. So we are basically in this space where we have pointer. Yeah? We have a left deep tree, we have a right deep tree, and with all these orders, how I label the leaves of those trees. But an actual join, I mean, a join as we considered it has a join predicate. So it may be that depending on how you label those trees, there's no real join predicate defined, and then your join predicate is true, equals true. And the join predicate equals true means that's equivalent to a cross product. Yes, yeah, the idea of a join predicate was to be selective in the first place. But if there's no join predicate specified, that is implicitly the same as saying, oh, my join predicate is true. Yeah? So whatever you feed into the operator, the result is true, and that means the join would produce a cross product. So in other words, if we use something like that, and then we say, okay, here A1, that is my D1 relation, and that is my D2 relation. However, there's no join predicate specified. What I'm doing in that situation is basically I'm throwing away this, I'm replacing this join here with a cross product. Yeah? That's basically what I'm doing in that situation. And the question is, should I even consider these things? Yeah? Shouldn't I say from the, I mean, come on, that's a cross product. The result has it's number of tuples from the left times number of tuples from the right. So the result will increase dramatically. I mean, wouldn't that mean, I mean, why should I consider that? Shouldn't I restrict my search to the situations where there is a join predicate specified between the inputs? Yeah, that's the question, and that's a big confusion in query optimization. You see that in many papers. And here's an example illustrating why you should consider those cross products. So here we have these 3 relations again, and here you see a plan on top that first joins F with D1, and then the result is joined with D2. Yeah. Here's another option. That's the only other option you have in the left deep plan, where you first join D2 with F, and then the result is joined with D1. And then there's this other plan where D1 and D2 are combined in a cross product, and the resulting plan is joined with F. Yeah? So the question is, should I, if you only look at cases where there's a joint predicate defined, you will be missing this plan here underneath. Yeah? And I made up some possible costs that you might see. So in this scenario, that's also called a star schema. That's very frequent. You see that very often in business analytics applications. So typically these tables, these central tables, that's called a fact table, is typically very large. And these tables outside, those are called dimension tables. That's why I'm using a capital D, tend to be very small. Yeah, and you see that here I made it up like, okay, this D1 only has 10 tuples. This F relation has 1 million tuples. And then you do the join and you have another 1 million tuples. So I don't have any selections here on the leaf level. So the intermediate result will be 1 million. Yeah, then you do another join with this 10 tuples. And you end up with 100 tuples in total, maybe, and so forth and so forth. Yeah? And if you do it in this order, first join with D2, it's a similar situation. So under the cost model we had last time, so this cost model that looks at the sizes of the intermediate results, yes? It counts up the number of intermediate results. So here the cost model means, okay, I add up the 1 million with the 100, and I get 1 million and 100, same here. 1 million times 100 is 1 million and 100, versus 100 plus 100 is 200. That's a huge difference. So you found a plan that's way better than the plans only, or the plans ignoring the cross products. Yeah? So here one has to be careful. Yeah? So it's really important when you do this kind of QRID optimization to understand, okay, the algorithm I'm looking at, is it also considering cross products or not? And if it's not considering cross products, how do I make it practical to detect these kind of situations where I would really find a much better plan? Huh? It's a long story, more for an advanced lecture. This is more like a warning saying, hey, think about what you're enumerating. Huh? In the exercise today, we will ask you to enumerate plans that ignore the cross products. Yeah, I think last week you enumerated everything, or the notebook I'm showing today will also enumerate everything, yeah, but you can also run these algorithms ignoring cross products. Okay, so with that, let's look at some terminology we will need for the notebooks, but also to understand what follows up in the lecture. One is join selectivity. So we talked about selectivity for unary operators. If you remember, there's a filter condition saying if selectivity is high, means few tuples are produced by the operator. Yeah? And if the selectivity is low, means many tuples are produced, so not so many tuples get filtered out. So we defined that for the unary selection operator. And we can also define that for joins. And that is how it is defined for joins. So basically you say the selectivity of a join operator, so the join of R and S, is defined as the number of tuples in the result of R and S divided by the number of tuples in the cross product of R and S. And that is obviously smaller equal 1. This is exactly 1 if that is equal to the cross product. So in a situation where the join predicate is true. Yeah, join predicate, whatever you feed in, is true. Yeah. And here's an example. So assume all of these relations R, S, and T have 1 million tuples each. And then you have selectivities defined among those for the joins. And then you basically can do the math, what that means. So we can basically now, depending on which join you do first, you have 1 million times 1 million would be the cross product. So 10 to the power of 12 tuples are in the cross product. However, you have this selectivity of 10 to the power of minus 9 times 10 to the, divided by 10 to the, multiplied with 10 to the power of 12, you get 1,000 tuples, so 10 to the power of 3, that survive. That's the number of intermediate results. So this is a very selective join. Yeah? However, in contrast here, you see the join of S and T with the same input sizes. The door's open. It's not that selective. Yeah? So 100,000 tuples are produced as the intermediate result. Yeah, so the size of the intermediate result is higher. And you see that then if you apply the cost model, you see again, okay, here this is a good situation, kind of good situation, 1,100, 1,000 plus 100. On the right side, it's 100,000 plus 100, so that's the total cost. So these two join orders have different costs under this cost model we used. Yeah? Okay. Yeah, let's briefly talk about predicates. So we had already these two different flavors of predicates. So predicates are expressions defined in the where or the on clause, for example. So this join on clause, yeah, that's another way of specifying the join predicates. And they are transformed to a conjunctive normal form. And basically the structure is like that. Yeah? So we have literals, those are the atoms basically, and we have clauses. Yeah? A clause is a disjunction of these literals, and the entire thing is a CNF form, yeah, of such an expression. But basically you had that in some other lecture, I suppose. And then we have the arity of predicates. So that only means you look at the number of attributes that are referenced in a predicate P. So maybe let's start directly with an example. So that's one attribute being referenced, attribute E from relation R. Yeah, so that has arity 1, but this is a situation where there are two attributes from two different relations being referenced. This is arity 2. Yeah, that's a join predicate basically, this one, and this one is a filter predicate. Yeah, so those are the two main things we need to differentiate. Of course, you could also have conditions phrased against three attributes from three relations. That's something like that. R.E plus T.B equals S.C. Why not? If that makes any sense to your application, whatever. That would be arity 3. Yeah? We will concentrate in the following on arity 2 and 1. Okay, so much about that. Yeah, again, I wrote it down again. Those are the special cases. Yeah, so we have this filter predicate and the join predicate. And here again are the examples. Had that before. Yeah, with that we can define what we call a join graph or query graph. So what is a join graph? So when you have a query in SQL, you can transform it into a join graph or query graph. And the idea is very simple. So all the relations that are mentioned in the query become vertices or nodes, in other words. The join predicates, they become edges, and the filter predicates are annotated to the vertices or nodes, if you want. Yeah, maybe let's look at an example to make that clear. So here are example join graphs. So those are, maybe let's start with this one on top. Yeah, so that's the join graph on three relations, R, S, and T. So here's a join predicate. Yeah, that becomes an edge in the graph. Here's another join predicate, that's another edge defined here, and so forth and so forth. Here's an example with four relations, R, S, V, and T. Here's a join condition, here's another one, here's another one. And of course, I mean, this is only a join. I mean, here I'm leaving away this dot notation. So typically, you could also write a dot notation. So this is typically something like V.E greater S.E. Yeah? This has to be a join predicate. And here you see those are the filter predicates. You can directly write the filter predicates to the nodes. Yeah? You basically attach that information at the nodes. So that's absolutely valid representation of the SQL statement. If you want to represent grouping and having a group by having, that's another story. So for the moment, we are just looking at queries that take a bunch of relations, join them, and produce an output result. So I'm ignoring group by aggregation, having all of this stuff and then more fancy operations. So it's very, you can also add that to join graphs, but I leave that away here for the moment. Yeah? So those are join graphs. Yeah, and right. Yeah, I think with that we can look at the two notebooks. So That is this first Picasso notebook I showed initially. And here you see a join graph, basically. And here you have 4 relations. No, I need the mouse pointer. So 4 relations A, B, C, and D. Here we also here we don't annotate the filter predicate, but the cardinality of those input relations. That's another way of doing it. And the edges, you see there are edges that are thick and others that are very narrow. That's just something we use for you to make it easier to understand which joins are selective and which joins are not so selective. Yeah, so for instance, this join edge here is not so selective because this number is relatively high. This means 37% of the cross product of the 2 input relations are selected. That's huge. That's many, many results. Yeah? Consider that the result is squarish in the result size, and we select 37% of some squarish result set size. That's a lot of stuff. Yeah? Here those are smaller, these numbers, and that's why the edges get thicker. Yeah? So the idea is to make the very selective edges pop out to show, hey, that's an edge maybe that could be useful to join on early on. Yeah? So that is what we have. And I know I'm on the wrong notebook. I'm kind of confused today. No, let's start. No, I started with that one. Sorry, got off with the wrong foot. Yeah, and now we want to look at plan alternatives in this situation. And one thing what we could do is we can, well, of course, we can compute a random order or a random query plan. Yeah? And then basically, if you say, okay, we only look at lefty plans, so we don't vary the binary structure of this join tree, all we have to find out is a labeling of those leaves, as I showed here on the slides. Yeah? If we go back to the slides. So basically, now we're here. What was that? Right, that's this slide. Yeah, this slide. So which of these orders am I going to use? How am I going to label this specific structure I focus on? I'm saying, okay, I ignore all of these binary structures for the moment. I just worry about, okay, in which order do I label those leaves? That's basically what's happening here. So I'm saying, okay, I use the order CBDA, whatever. Yeah? So that's basically what this cell is computing. And then I can draw that random plan. CBDA, that's the lefty plan. That would be the order. And now if I need a cost model to find out whether that is a good plan or a bad plan. Yeah? And that's basically what I'm doing here. So I have a very simple cost function saying, okay, whatever the cost is, I just add up the size of the left input and the right input for the moment. So I need a function that computes the cost for a given plan. Yeah? So I have a plan, I have this query graph, and I have my cost function. And with that, I can compute the costs. So for this plan, the estimated costs under my cost model are 1,298,000 whatever. Again, those cost estimates typically don't come with a unit attached. It's not seconds or joule or something like that. It's some placeholder, some abstract domain where I believe if the number is big, it's bad. If the number is small, it's good. That's typically all what query optimizers do at that point in time. Yeah. And now I can actually do that in a Monte Carlo style. Monte Carlo algorithm? There was some nodding. So what is Monte Carlo algorithm? Monte Carlo algorithm means you somehow throw a dice. Yeah, so you randomly do stuff. You randomly create an option and do a calculation for the option. And that's a very important algorithmic paradigm you see in computer science. And I'm doing it here. I'm saying, I'm too lazy to enumerate all of those possibilities. I just throw the dice. In this situation, I throw the dice 4 times and see what I get if I randomly choose these orders. So I have random orders, and you see the costs for this random order is 1 million. Oh, it's below 1 million. This is 2 million. This is 100, oh, that's quite different. So more than one order of magnitude difference in cost already just by randomly doing these things. Actually, that's a valid algorithmic approach to randomly do these things. So to randomly produce plans, in particular, if you have an SLA saying you're only allowed to do query optimization like for 10 milliseconds. Yeah, if you cannot exhaustively enumerate all of the options, then it's a valid approach to sample, to randomly pick some of the options and cost only those. Yeah? You won't find the globally optimal solution, but maybe you find something that's better than just picking the first plan that comes around the corner. Yeah, and then you can do exhaustive enumeration, of course. Yeah, so basically this factorial thing. So what is the cheapest plan? So it's actually pretty fast here. So the cheapest plan only has 61,000 costs, so that's 2 times better than the random plan we computed before. Yeah. Okay, so this is easy to do if you only have 4 relations, but what happens if you have a bigger scenario, like going back to our IMDb scenario? This is the join graph for the IMDb scenario, and assume that all of those relations are now mentioned. So what is the best way to join those relations? Again, I'm ignoring the binary tree structure. I'm just looking at the options I have for labeling those leaves. And then if I run that, that may take a while. I think that takes roughly a minute on my machine, because now I'm going through these number of relations, factorial number of plans, and I cost each plan, and I pick the fastest plan or the best plan under the cost model. So we have to wait a little bit. Of course, this is Python. If you do that in C++, the constant will be better. But again, this is an exponential behavior. The more relations you add, the more it goes through the roof. Come on. How many relations do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so 10 actually for C++ implementation is like nothing, would be super fast, but for Python, it's completely killing it. Here we go. So that's the fastest plan, the fastest left deep plan. Yeah? So it took 48 seconds, and that is a left deep plan, and this is the cost that comes attached. That looks big. Doesn't look so good, right? Yeah? Okay, and what you should be doing in the exercise today is do the same thing, basically modify this notebook to only consider plans along edges existing in the query graph. Yeah? Not looking at the cross products, ignoring the cross products, but only considering plans where relations are actually can be joined. Yeah? Situations where there is a join predicate specified between those two relations. That's basically the exercise you should be doing. Yeah, so much about that. The other notebook I wanted to show is this, what's called a Picasso visualization. And we'll see in a moment why it is named like that. So here we have a similar situation as before. We have different, it's a bit easier. So basically the query we are looking at is actually a very simple case. So we just have 2 selection operators, one with this predicate P and the other with predicate Q, and we have one input relation. That's the only query we're looking at here. And the question is, how do I execute that? Do I first filter on P? Do I first filter on Q? How do I access the stuff that sits in R? So again, you have the option to scan all the tuples from R, or you have the option to use whatever index. If you have an index that can be exploited because the filter predicate is specified against the index, as explained last time with the B trees, well, then you should use the index. So basically, the logical plan is something like that. You could invert these 2 bubbles, of course. Yeah? And the question is, how do we do that? So we have a number of options for the physical plan. Yeah? So translating that into an algorithm, translating that into whether I use index, access, or scan. And for all of these options, I computed I define cost models. So without going into detail here, so for all of my plan alternatives, like with the supermarkets, now I have a cost model. Telling me, okay, that's going to cost that much. Cost meaning not only what I spent in the supermarket, but also the time spent sitting on the train. All of these costs are like combined into one number. That is what these cost models are doing. So basically, I can then try to visualize that. And what I'm doing here, maybe I'll remove some of the graphs here to make it easier to digest. I have a method here, for instance, that's oops, make it a little bit smaller. A method that uses an index to access the data. And what I'm varying here on the x-axis is the selectivity of this filter predicate P. So recall how many elements are produced by that operation. So the more you are on the right, the more tuples are produced. Again, here this space means low selectivity. Not many tuples get filtered out, whereas on the left, this means high selectivity. Zero meaning everything is removed, no result is produced. So that's the selectivity. More results here, and then you get the cost estimate for this specific method. Yeah, and then you can basically do the math for all other physical plans you have. So maybe maybe full scan, yeah, maybe something like that. And then you see, for instance, here that that's the difference of a full scan versus an index axis. So the full scan looks like, okay, whatever I do, independent of the selectivity, that's a constant. Yeah, it's always the same cost because I always have to read all of the stuff from the relation, and it doesn't make a difference whether the selectivity is low or whether the selectivity is high. In contrast, you see for this index, it makes a huge difference. So the cost estimate varies a lot depending on whether it's a high selectivity or low selectivity. That's the kind of graph you could draw. But what happens if you want to vary both of those selectivities? So again, we have two filter predicates on P and Q. And how would we visualize that? And that is done by Picasso diagrams. Just show how it looks directly. So here, how you read that is on each of the axes, and you could actually also do that in 3D. On each of the axes, you write the selectivity, you write one of the dimensions. So one is this selectivity parameter of predicate P, the other is the selectivity parameter of Q. And then the color indicates what is the best plan at that point in time. So if you're highly selective on both P and Q, you're somewhere down here. If selectivity is low on P, selectivity is low on P, but the selectivity is high on Q. That's basically this point where the cursor is currently. Then I should use this plan here. Shown here. And this is a very useful tool to explore the options an optimizer has and the different planning alternatives. And here's an example that illustrates how these how the space may be changed depending on the constants you're using. So basically, the cost models typically have to factor in how much does it cost to compare two elements? How much does it cost to read stuff from disk and so forth and so forth? And in the cost models in the notebook, I'm using these constants. So I say a sequential read of one tuple costs 1. A random read costs 100. A comparison costs 0.001. And that's my table size of I have 1 million tuples. And now what I do here in this loop is I vary the costs I have for a random read operation. So randomly going to a dedicated position on SSD, on hard disk, on tape, on DRAM, whatever storage medium you are using. I'm changing, I'm looping over the random read cost. And then you see how these costs actually change. So for instance, here, in this first plot, you see the cost for random read are only 10 times higher than the cost for a sequential read. Okay, So here's a huge space where these red planes make a lot of sense. So what is the red plane? Again, the red plane is some sort of index. Yeah? Some sort of index axis is as soon as the selectivity goes beyond 0.2 for both cases, for both predicates, you should be using an index. That is what this plan is saying. If the selectivity is higher, you should be using one of those other index plans. So all of those are index plans, basically, different types of index axes. There's no full scan plan that can compete in this world. And now if you increase the random read cost, you see that your options will change. In particular, you will see in this world here, where the random read cost is relatively high, all of a sudden you see, oh, there's this purple stuff bubbling up here. And what is purple? Well, purple is a full scan. Yeah? So in this space here, if your selectivity is on this space, the index doesn't pay off anymore. All of a sudden, blindly scanning the data is more efficient, is the best plan, is better than the index axis. Yeah? And that's actually a phenomenon you see on certain types of storage media. Yeah? Back in the old days, people used hard disks, yeah? Mechanical devices where you had spinning platters, and the random read cost was insane, was insanely high. Yeah? We're still using that for like backup devices, but not for real systems anymore. So real systems use SSD, DRAM, persistent RAM, whatever. Yeah? But in those systems, it was really critical to make a right decision. It was actually a problem there that if you made the wrong decision, if you make a decision to use the index, you could be by orders of magnitude slower than not using the index. Yeah? An index can only be faster, right? No, it can completely ruin your performance if the index is mapped to a storage medium that is really bad on random access. And therefore, in terms of a database system, it's super important to model the access patterns correctly in your cost models, because otherwise you will be screwed in terms of performance. Yeah, so I invite you to look at those two notebooks because they explain the gist of what the difficulties are in cost-based optimization. So now, if you think back again, okay, now we looked only at left deep trees, but what if you look at the other binary tree structures as well, and what does that mean for the different cost models, or for the costs we obtain? So if you look at the plan space for these three tuples, yeah, we know, okay, we have these binary trees. Yeah, this is the left deep tree, right deep tree, right deep tree. We have these different enumerations, there's different labelings here. That should be 6, of course, for each of the tree structures. But just if you look at these options, you will see there's no real difference in the costs here. So all of these 4 plans have the same costs in the cost model. So in particular here you will see whether you have this subplan RNS or that subplan. So here S is on the left, that's why it's labeled left, and R is on the right. The same here, S left, R right. Same here, R left. Yeah, that is basically what these rows mean. So this here, it doesn't matter whether S is on the left or R is on the right, because under our cost model, we only look at the number of results produced by the join. So it won't make a difference whether we put S left or we put S on the right. Yeah, that's symmetric. Doesn't make any difference. However, then there is reality. And in reality, you will eventually use an algorithm. And here's one of the most important join algorithms that's used in practice. It's really relatively easy to understand. So you have two relations, R and S. You have a join predicate specified on those two relations. So it's some equality predicate, R.x equals S.y, for instance. So how do you compute the join? In different phases. If you first create a hash map, you create this result that you want to produce, so basically a set for the result. And now what you do is you first create a hash map over the left input, which is relation R in this example. So basically you loop over all tuples from small r and capital R and insert that tuple into the hash map. And the trick, of course, is here the key to use in the hash map is that same attribute you're using in the joint predicate. Yeah? So basically create a hash map on r.x and insert as a value the tuple having that key. If you have more than one entry that has the same attribute value on r.x, you have to be careful. Then you have to operate with sets. Yeah? But for the sake of simplicity, let's assume there are no such duplicates. So then comes the second phase, and that is basically probing S against the hash map. So now you loop over all tuples from S, that's the right input in this example. And for each of those tuples, you send a query to the hash map. Basically, you probe the hash map whether it has an entry for attribute value s.y. Why s.y? Because that's the equality condition. Yeah? So like that, you find all tuples from R that have the same value as this S tuple in Y. Yeah? So basically, the equality is solved by looking directly into the hash map. Yeah? And basically, whatever the result is here, you add that to that set. And then you have to basically create the result set. So if the tuples returned here, so if that set is not empty, that's basically what's checked here, you add the tuples in that set, cross product this tuple to the result set. Yeah? So basically that's what we also saw and how joins are computed, how join results are computed. Yeah? So very simple idea. You create a hash table on the left input using the key from the join predicate, and then you probe each and every tuple from the right input, that's the S relation in that example, using this s.y part of the join predicate to identify the results. That's a very efficient algorithm because you have linear costs for creating, or linear in the number of tuples from R to create the hash table, and then you have another linear costs in the number of tuples from S to probe that hash table. Yeah? Of course, I mean, if the join predicate equals true, you can't do something with the hash join. However, the hash join works super well if there's a foreign key constraint, which are typically equality constraints specified. So basically, that is the most important algorithm that can be used in almost all kind of situations in databases, and it works super well. Yeah? And now if you look at that algorithm, so here again, that's the runtime expressed in the cost model. So here I'm saying it's, okay, there's some constant, basically, constant cost for inserting something into the hash table, that is the C1 value, times the number of tuples in R, plus another constant C2 times the number of tuples in S. That is the cost for my join. Yeah, that's how I model the total runtime of a hash join. So those are two linear factors in that cost model. And these constants C1 and C2 depend on many, many factors actually. So if you learned that, yeah, for most hash tables, it's roughly on the order of 0.01. If you look at the constants, if you look at real implementations of hash tables, there are orders of magnitude difference in performance. We wrote a paper about that a while ago where we illustrate how important it is to pick the right hash table in such a situation. It's really not some percentage, but it's orders of magnitude. You can be faster in a hash join if you choose your hash table and your hash functions in particular well. Yeah, but for us, it's important to understand that, so this is not, so if you have a cost model like that, so the order now all of a sudden makes a difference, whether one relation is the left input or the right input or the other way around. Now it makes a difference. I mean, if these constants are equal, that's basically this bullet point here, it doesn't make a difference. It's okay, it's still the same cost. Yeah? But if one of those constants, but if these constants are different, yeah, then it makes a difference and you will get different costs returned from the cost model, whether it's in this order or in that order. Okay. And then there's another aspect with this hash join algorithm, and that is, assume you have a cost model like main memory. Yeah, so you want to, you don't have arbitrary amounts of main memory available, so you want to make that part of your cost model. So that could be a model like this. Yeah? So your main memory model could be something like this, saying, okay, I have two constants. One, C3 is the overhead of the hash map for storing an entry. Yeah? So typically the hash map will store the actual data plus some structural, some overhead data, some metadata in the hash map. So it's basically the size of the tuple of R in bytes times some overhead. So this would be something greater equal 1 somehow. Huh? Greater is or strictly greater 1 typically. Yeah? And with that you get times number the tuples in R, yeah? Because you build the hash map for all of the tuples in R. That gives you a cost estimate for the main memory you spend. Well, and here comes a surprise. There's no S being mentioned here. Yeah? This is just about R. We don't care about S, yeah? Because the idea of a hash join would then be, okay, I mean, I can probe the tuples from S one by one. I don't have to really store all of the input relation of S in the operator. I can just probe them one by one. So I don't have to model the memory costs for that. So the size of S plays no role in this cost model. And that also implies directly that it is advantageous in this cost model to take the smaller input relation as the left input relation. Yeah? If you have one relation has 1 megabyte and the other has 1 terabyte, well, you better build the hash map on the 1 megabyte relation and not on the 1 terabyte relation. Yeah? That also means that this, if you only have limited amounts of main memory available, yeah, and you have one relation that fits in your main memory and the other does not, build your hash map on the relation that fits, yeah, and probe the other relation against it. Yeah? So then you have a join operator that can join tables where one of the tables doesn't fit into main memory, for instance. Yeah? So it's very important to choose that wisely, and the typical choice is to use the input relation that is smaller, yeah, to the left, to build the hash map on. But in any case, what that means is this hash join is asymmetric all of a sudden in this cost model, not symmetric as before, where we only looked at the size of the intermediate results. Now it's really asymmetric if you factor in the main memory consumption of these operators. So things get more complex when you look at these operators. Yeah, and here's how I visualize that. Now I don't annotate the edges, but basically I make a small box here at those operators, saying, okay, here, if you use S as the left input, well, yeah, then you have to build a hash table on S in this hash join operator. And that will be the costs for that, yeah? 1 million times those constants, whatever. Yeah, but it's basically 1 million tuples where you have to build the hash table on in that operator. The same holds here. As this operator only produces 1,000 tuples, here in this operator you will only have to create a hash table on 1,000 tuples, yeah? Because that is the 1,000 tuples produced by this operation. Now if you look at other structures, you will see how. Here, this is 1 million, that is 1 million. So here you spend in total 2 million tuples times those constants for hash tables. Yeah? So in terms of memory, those plans look much better than those plans. So we're seeing a difference. Yeah? So it really makes a difference now. It's not the same costs for those plans anymore. Yeah, I depicted the costs here. So whatever, that's 1 million, 1,000, 2 million times those constants. So obviously, this stuff is better in terms of memory. And now if you have that, you can start, okay, sure, I mean, I combine those cost models. So you could say, okay, now I look at both the memory consumption and the number of intermediate results being produced. That's what I'm trying to depict here. Yeah? So I annotated the edges and again wrote down what is the main memory consumption. And yeah, basically you have something like that, where you have this a combined cost model. And then basically you have a weight for each of those individual cost models. So C5 and C6 are weights where you say, okay, I'm focusing a bit more on main memory or not so much on intermediate results. Depending on how you want to optimize, depending on which system you're running on, you can set those weights yeah, to fit your purpose. So that's how you could combine those cost models. Yeah, and then it's time to think about reality. Again, I said that already before. So we're in a world where we create a model. And if you create a model, from time to time, you should check back with reality. Is what I'm modeling really, Does it have a link with reality? Is it really reflecting reality? Is that doing what I believe it's doing? And yeah, there's an issue here. Because, so let's assume T is joined, so it's the right input to these operations. So here T is on the right, here T is on the left. And we have modeled it like that in this case, T does not trigger any additional storage cost. Yeah? If you look at the model, we said only the left input is going to be considered because the left input will be used to create the hash table on. Yeah? So in T, you can basically, it's in a streaming fashion, just tuple by tuple. You probe one tuple, produce the output, and then you can look at the next tuple. But that, it doesn't make any sense to like store all of the tuples from T in this operator. That doesn't make any sense algorithmically. Yeah? Right. However, then if you look at an implementation, and let's say the implementation we did in these simple notebook examples, you will see something like this. So our implementation of this join, hash-based equi-join operator, with this symbol, has an evaluate function. And what does the evaluate function do? Well, before running, in order to evaluate the result to the join, it calls its inputs. So there's a left input, there's a right input. And what these functions will be doing, they completely generate the results. They completely materialize those results in main memory. Yeah, so which actually means here is memory costs that's being triggered with that. That does not correspond to what we had in mind when looking at the hash join algorithm. Yeah? So the implementation is doing something different. Yeah? So there's a mismatch. Yeah? So the model we had in mind doesn't correspond to our implementation. Well, and then we have two options. We can change the model, so we can change the model to reflect what we're doing in our implementation. Yeah? So if that was our initial model, only modeling main memory costs along the size of input relation R, so the left input relation, we could now change it to say, okay, yeah, that's not true, sorry for that. Yeah, so we will use this model as before, plus we add some C5, some weight times S, yeah, so this is again something greater 1. Now that's the size of the tuple, and you don't have to add storage overhead here actually, because you just probe it one by one. So it's just the size of the tuple times the number of tuples. That would be the additional memory cost, and that would be saying like, yeah, I assume that all of this stuff gets stored somewhere in main memory. Yeah, that's what you could do. You could change the cost model. That's one way of doing that. But the other way of doing that would also be to change reality. Yeah, that's a nice thing about computer science. We don't have to live with physics and chemistry and biology. We can ignore that. We can create our own worlds, our own universe. And that's, in this situation, actually the better option. So as we saw in the implementation, that we materialize those tuples. So in other words, we really create those tuples and store them in main memory. We can change the implementation. Yeah? And you see that when you worry about these algorithms that process data, there are situations where you can make decisions one by one, and there are decisions where you can't make decisions one by one, or in other words, tuple by tuple. For instance, for a selection, I mean, just by inspecting a single tuple, you can make the decision whether it qualifies or not. Yeah? That's how we defined it actually. You have this filter predicate, you feed in a tuple, and the predicate will tell you, yeah, that's good or that's bad. You don't have to look at the entire data set to make that decision. The tuple is just fine. The tuple alone is just fine. So that's a great point in a pipeline to just look at individual tuples. However, there are situations, for instance, if you do an aggregation with a maximum, that might be more difficult. Yeah? I mean, you cannot, based on a single tuple, you cannot make the decision whether that is a maximum or not. You have to look at all of the tuples. Yeah? If you look at the tuple, you can make a decision whether that is the maximum of the stuff you've seen so far. That is okay. Yeah, you consume 10 tuples and you can make a decision, yeah, from the 10 tuples I've seen, that is the maximum. You just always keep the maximum. Yeah? You get a new tuple. If that is bigger than the maximum you've seen so far, you replace it, and so forth and so forth. So that leads to a notion of what we call pipelines and pipeline breakers. Your pipelines you may know from like Unix style pipelines where there's this pipeline pipe symbol in between the shell script commands. And a similar thing exists in databases. So basically, when you have a plan like this, and the plan is implemented through these hash joins, what that means is when you start building the hash table, yeah, you start building the hash table on this left input, which is relation R, that means nothing really happens. You're just consuming all of this stuff here and materialize it into the hash table. But now if you start doing the join here with S, you take one tuple of S, probe it against that hash table, and whatever the results are, you can directly continue, you can directly deliver it up to the next operator. So basically, programmatically, if you probe a tuple from S here, that will produce some results, and you can directly insert those tuples into the hash table in this operator. Yeah, there's no need to like first assemble all of the join results here, or first somehow, or get first all of the tuples from S, yeah, and once you got all of the tuples from S into the operator, then you start probing the hash table you built on R, and then you create join results. That's not necessary, yeah. You can directly ask S, hey, give me the next tuple. Yeah, then that tuple will be probed against the hash table. If you find that there are join mates with R, those join results are directly inserted into the hash table. Yeah, that is how you can run a pipeline like that. Yeah? So there will be points where you block and others where you don't block. Yeah? And here, again, in the second operator, you first have to completely exhaust all tuples, exhaust relation S, yeah? Probe all tuples from S against that hash table, produce all join results of that operator, and only when you're done with that, you are done creating this hash table. Yeah? And then, only then you are allowed to start with T, tuple by tuple, probe tuples from T against that hash map, and then directly produce the results and deliver them to whoever consumes those results. Yeah? So that is something you see in those pipelines. And yeah, depending on how you organize, whether it's right deep or left deep, you see here, I mean, you can first do something here, but okay, in order to fill this hash table, and you first have to process S. In contrast, in left deep, you could actually concurrently create those two hash tables if you want, yeah, in two separate threads. And then once you're done with both, you just stream the data from S along those two hash tables. That's different behavior in terms of pipelining. And that leads to a concept that we call plan sections. So basically, plan section mean I'm now dividing a plan along its pipeline breakers. Yeah? So I know here's a pipeline breaker because I have to create a hash table, so this becomes one section in the plan. Then there's another section, that's this one. That's basically streaming data from S along that hash table into this hash table. That's another pipeline. And finally, there's a third pipeline, A3, that just streams the tuples from T along that hash table to the user consuming that result. Yeah? And you see, depending on which tree structure you use, you will get different, different segments, different sections of the plan. Yeah, that was the time. Yeah, and then basically you can reason about the quality of those plans in terms of pipelining. Yeah, and then you can make decisions like, okay, if the size of the join result of R and S is smaller than the size of T, maybe that is a good plan, and the other way around, that's a better plan. These kind of things. So things get even more complex. But what's now really important is the next step. So I mean, I was just trying to give you a feeling for the search space or the complexity a database optimizer has to tackle when coming up with a certain plan. Yeah? So eventually, a query optimizer will make a decision for a plan. Yeah? Assuming, I mean, it could be something like this. Yeah? It could be like this plan. Eventually, we say, okay, that is my tree structure, and that is how I label those leaves in my tree structure. I'm going to go for that plan. Then the next question occurs in the query optimizer that is, okay, fine, that looks good. That is the slide, right? But how do I get from a slide to actually code that I can execute? Yeah? That's just a concept so far. Yeah? Somehow represented in a data structure in the optimizer. But hey, I want to execute code. I want to really execute code that produces a join result. So how would I do that? And there again, things get, again, there are options. Yeah? So basically, we want to generate code that executes, that does the stuff that the query is supposed to do. And one way of doing that is actually create LLVM code or WebAssembly code. In that step, you could also generate C++ code and then compile it. So it's really close to what a standard compiler would be doing. You have in standard compiler, you feed in C++ or Rust or whatever you want, yeah, and then produce binary code. And it's kind of the same thing here. So database optimizers generate code, just as C++ compilers like Clang, and GCC and stuff produce code. So we have a similar thing we're doing. However, there's an important difference when you look at how language compilers, I mean, if you produce a software, you generate some software, you don't really care how long it takes to compile the stuff. Well, it's nasty if it takes very long, but you don't really care because you only do that once. Yeah, then you ship your binary and then you only work with the binary. So the costs for compiling the stuff don't hurt that much. Here we are in a different world in databases because think about what happens. So the user or whatever application on top sends a query and expects the database system to deliver the result quickly. So the compilation time is part of that. Yeah, so we receive the SQL query, we have to quickly inspect it, do all the transformations, maybe rule-based, transform it to a query graph, do the plan enumeration, come up with a physical plan, generate the code, execute the code, producing the result, delivering the result. That has to happen all very quickly. Yeah? If you are bad on like compiling, if compiling takes forever, then the overall query time may be so high that we like kill all the advantages of compiling it in the first place. Yeah? So that's an additional challenge we have here. And that is, for instance, the reason that typically database engines don't generate C++ code. Yeah? If you really generate C++ code, then it has to be parsed again, and it takes longer, and it's typically not a good option. So it's typically better to generate something like LLVM, not in the textual format, but through the API, like in Bitcode or something, or use WebAssembly. So we did something with WebAssembly recently. So WebAssembly is really kind of assembly code that runs in your browser, but the fun thing about that, that's not only for the web, but you can use it for database systems. And we just had a paper on that where we show why that makes a lot of sense, actually. It can be really fast using WebAssembly. So now our initial graph, our overview graph, get even more complex. Yeah? So we are in this space where we had the canonical plan, then we had that iterative application of rules, then we enumerated plans, and now we found a plan, and now we have these two options. Basically, you generate real code using LLVM, WebAssembly, whatever, or you use physical operators. That is what we're doing in the notebook, actually. And that one of those options basically represents the program you're executing to compute the result. So important is this slide. Those are the two options you have at this point in time. Yeah? So you can either interpret the plan. That's what we do in the notebook. So we don't generate real code. Yeah? But when you execute the operators in the relational algebra library of our projects, yeah, that is what you will be doing. Yeah, there's no code generation going on. So the physical operators are converted one-to-one to programming language constructs by calls to a library of physical operators. So basically each of those physical operators has a method like evaluate or execute or something like that, and there the algorithm is written down. And that's what we call plan interpretation. In contrast, code generation generates program code, as explained before. And that also has the effect that this boundaries, yeah, so if you think about the plan structure, you have this physical operator, physical operator, physical operator. And I mean, each operator has its boundary in this object world. In code generation, we throw away most of those boundaries, as you will see in a moment. So how does that work? Here's an example for the plan on the right. Yeah? So again, those 3 inputs, we have 3 of those sections, A1, A2, and A3, and that is the code you could generate for that. Of course, in WebAssembly, LLVM, whatever, that's only the pseudocode. But you see how that breaks the boundaries. In particular, it breaks the boundaries for these join operators. Yeah? So this filling the hash table part is done in A1, probing the hash table part is in A2, and also filling this other hash table 2 part is done in A2. Yeah? In the code, that means, okay, A1, for all tuples in R, you make an insert in that hash table. So not much, that's all that happens there. Then in A2, for all tuples in S, you probe hash table 1, this one. If there's a result, you insert it into hash table 2. And then finally, A3, for all tuples in T, you probe them against the hash table 2, and if there's a result, you produce it. Oops. That's visualized here through this yield function saying, okay, whoever receives the results, here directly pass it on without materializing it first. Yeah? That is how code generation in a query optimizer works. Okay, yeah, so far so clear? Questions? Not many questions today. Yeah, and from that then there are also other options. As I told you, you can now worry about resources, you could execute, you could worry about adding more threads, for instance. So this is a single-threaded plan. You could say, okay, I make that multi-threaded. For instance, you could use 4 threads to fill the hash table. Of course, then you have to make sure that the hash table is thread safe. That can be done relatively easily through hash tables that have a compare and swap operations that basically transactionally allow you to insert in a specific slot in the hash table. So that's a relatively good idea to do that. And then you can do the same thing with probes. Yeah? So you have one thread looking at like 1/4 of the input and then probing that hash table and then inserting it here again. Of course, once you're done inserting, yeah, actually the hash table doesn't have to be thread safe anymore. Yeah? For a read-only structure. At this point in time when you're probing, it's a read-only structure. So of course, before it had to be thread safe to fill in the stuff, but once you're querying, whenever you're in a situation where you only read data, you don't have to worry about stuff being thread safe. You don't have to worry about concurrency control. Reading is fine. Multiple threads, only reading, no problem whatsoever. The problems start if one of them starts to write and update things, then you're in trouble. Different story. Yeah. Okay. Yeah, here I will skip over that. So I mentioned that before, Spark is a very popular framework for processing large data sets. And when you look at how Spark works, it's exactly what I explained so far in this lecture. You also have the option in Spark to look at the logical plan and the physical plan here, and that's the physical plan here, and you will see all the operations and all the tricks I explained here in this lecture so far. It's really state-of-the-art what you're learning here. So that's how Spark is doing it. Okay, so to wrap up. So what do I do if the queries in my database are too slow? So how do we actually get from SQL to an executable program in principle? Through automatic heuristic and cost-based optimization. And actually you don't have to worry about that much. However, keep in mind, different systems have very different query optimizers. Yeah? In general, the more you pay, the more sophisticated the query optimizer will become. Yeah? So it might be worth considering using a different database system if your queries are too slow. So what are the tasks of cost-based optimization? Yeah, from this logical plan to a physical plan, to enumerate and evaluate plan alternatives. You try to come up with cost estimates. You choose join order, you choose physical operators, you plan the pipeline. What do you do with blocking versus non-blocking operators, and also the main memory costs involved in that. And you can also, if you want, reason about, okay, how many threads to assign to which section of the pipeline. So those are the tasks an optimizer can do. And then there's this divide whether you do code generation or not. So you can interpret the stuff. That's one way of doing that. And plan interpretation was actually pretty popular in databases that operate on disks. So a system like Postgres was initially designed for working on hard disks. And there the main cost was accessing the disk. Writing to disk, reading from disk was killing everything. It didn't make a difference whether you had code generation or not, because the disk was killing it anyway. But starting with the 90s, people made the transition to main memory systems. And there it made much more of a difference whether you generated code or not. And what was a real game changer. Yeah, for all of these topics, we actually only scratched the surface. There are many more interesting techniques in this field, and they directly lead to what we're doing in terms of research in my group. So in terms of literature, if you want, there's some videos from the database core lecture if you're interested, but some of that will be repeated in the core lecture, of course. And there's a book I wrote about that eventually that's more like an exercise book around those videos, but it summarizes very well the main takeaways from query optimization. But in general, there's a core lecture, database systems, where we go more into detail in that. Yeah, with that, that's what I wanted to tell you today. See you next week. No, next week is a holiday. So 2 weeks from now. Okay, enjoy the holidays. Thanks.